I should reiterate that while the Maxwell-Boltzmann statistics don't apparently fit any known particle, the theory is vibrant and rich. It has contributed to a rich, robust theory, a kinetic theory of gases. It has given meaning and a deep insight into the phenomenon of temperature. So this is actually a huge advance in physics as a whole. But at the particulate level, at the quantum mechanical level, it apparently does not hold as advertised. The next step in the understanding of where to go from here was provided by two other luminaries, giants of the 20th century. The first, Satyendra Nath Bose, was an Indian physicist. The second, Einstein, was Einstein. Bose proposed a way of viewing assemblages of photons, quantized particles of light, and figuring out what the assemblage would do. The theory that he proposed was not immediately popular. In fact, it was rejected at the first journal he sent it to, but it found support with the redoubtable Einstein. Einstein realized that Bose's ideas could also hold or apply to assemblages of larger elements like atoms, and together they published a sequence of papers starting in 1924. These papers articulated a model for certain physical particles. Now, what was the key insight? Well, let's go back to our toy example to see what Bose and Einstein discerned in the physical world. So, the setting is this. We are thinking about the random placement of a certain number of balls, n, in the example, n is 12, into a certain number of urns, r, and in our example, r is 4. The question, the thought that came across Bose's mind was the following. What if the balls are not distinguishable? This is strange. We don't quite have an easy analog of this in our practical experience. For example, imagine tossing a coin twice. Well, naturally, I know what the first toss was and what the second toss was. The experiment is equivalent to taking a pair of coins and tossing them. Of course, I know this coin is separate from this coin. And therefore, for that experiment, the possible outcomes are 4 in number, labeling, for example, the coin on your right as coin 1, the coin on your left as coin 2. You have heads, 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 tails, 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 and tails, heads. But in Bose's view, if the coins were indistinguishable, then you could not discern a head and a tail from a tail and a head. So in this view, you only have 3 possible outcomes: a head-head, a head and a tail, and a tail-tail. It's as if you have a triangle of outcomes, and your experiment is giving you one side of the triangle at random. This is strange. Okay, how do we grapple around this? And in particular, how do we figure out occupancy configurations in this kind of non-intuitive setting? Well, we adopt as a guiding principle the sage advice of the Hungarian mathematician George Polya, who opined that in complex problems we could do worse than asking the following very, very simple question. What is the simplest version of the problem that I do not yet know how to solve? Of course, in this case, I've got too many balls and too many urns, and so I'd want to reduce the number of balls and the number of urns to see if I can discern essential features. Well, how many balls should I have? Well, 1 ball, well, that is trivial, so perhaps I should start with 2 balls. And how many urns? Well, 1 or 2 urns appears trivial, so perhaps we should start with 3 urns. And so we have a sanitized, simpler setting. 2 indistinguishable balls, and 3 urns. And now I want to distribute these balls in these urns. Of course, this problem is now easy to handle. Let's go about stripping it of spurious structure, which is not essential to the logical heart of the problem. What is important about the urns? Is it important that I actually give you an urn? No, that doesn't seem to be critical to the problem. A sanitized view of, let's say, cells, rectangular in form, are quite sufficient. All I need is a place to put balls. Is it important that I have floors and ceilings for these cells? Well, even that is not important. All I need to know is which urn is which. And so imagine the following way of setting up the problem. Stack up your urns from left to right. Well, at the left end, you have a wall. This is the edge of your first urn. At the right end, you have a wall. This is the edge of your last urn. In between, we have walls, separators, or sticks. And these sticks serve to separate one urn from the other. And now what do? We toss the balls into the urns. The example I've shown you is where the first urn is empty, the second urn has a ball, the third urn has one ball, and so we are looking at the occupancy configuration 0, 1, 1. In this model of Bose and Einstein, it makes little matter whether the first ball has gone into urn 2 or into urn 3. All that matters is that the urns 2 and 3 are occupied each with one ball. The moment I understand this, now I can start writing out all possibilities. I'll pause for a moment and let you play with this and see whether you can write down all the possible configurations that could result. Now you've had a chance to play with it. Did you come up with a representation like this? Well, what have we done here? The simplest way to do this, and the most efficient way, is to be very systematic in the way you go about assigning balls to urns. In other words, do it in a lexicographic fashion. One way of thinking about the assignment is as follows. We have 2 balls. One possibility is that both balls go into one urn. Now, if that is the case, we have the situation that is seen on your left. You have urns, one being occupied with 2 balls, with occupancy configuration 2, 0, 0. Or urn 2 with 2 balls, occupancy configuration 0, 2, 0. Or urn 3 with 2 balls, occupancy configuration 0, 0, 2. Now we've exhausted all possibilities for both balls going into a common urn. We can now turn our attention to those cases where no urn has a double occupancy. But in this case, we can start by saying, well, what are those cases where the first urn has single occupancy? In which case, the remaining ball has to go to either urns 2 or 3, leading to the occupancy numbers 1, 1, 0 and 1, 0, 1 respectively. At this point, we've exhausted all possibilities for single occupancy or double occupancy of the first urn, which means the first urn can now only be empty as the last remaining case. But now, since double occupancy is forbidden, that brings us back to the example we started with, the occupancy 0, 1, 1. And now it is clear there are no other cases, and so this is the universe of possibilities. Now, we want to extract from this simple example key features which can generalize to arbitrary structures. So let's take a hard look at what these images are telling us. At the ends, I've got these urn boundaries. They are fixed. Now, the urns themselves are metaphorical urns, and remember, they are infinitely distensible. An urn can contain as many balls as you wish, right? And I denoted this in the figures on your left by showing urns which are big enough to accommodate 2 balls. So I just moved the barriers to make sure I could put 2 balls in. Good. Now, if I look from left to right on your screen, what do you see? I see that I have a succession of balls and urn barriers. Let's rephrase this. The balls look like stones. The urn barriers, the separators, look like sticks, or if you like, zeros and ones. I've got a string of sticks and stones in some order. Each of the cases gives me a distinct arrangement of sticks and stones, ones and zeros. What appears to matter are the positions that are available. How many positions do I have? Well, I've got 2 balls, 2 stones. And how many sticks? Well, there are 3 urns, and therefore the separators are 3 minus 1 or 2 in number. So I have 2 sticks, 2 balls, 4 locations. And our 6 possibilities have covered all ways of distributing those 2 balls into those 4 locations. Okay, this is our key insight. Right? Let's capture everything together. We've reduced the problem of distributing our 2 balls into our 3 urns into the following consideration. There are 2 identical stones, balls, which are indistinguishable. There are 3 minus 1 or 2 sticks which connote cell barriers, urn walls, or separators. Together, I have between the sticks and the stones 2 plus 2 or 4 locations. And of those 4 locations, I have to specify which 2 the sticks land in and which 2 the stones land in. There are exactly 4 choose 2 ways of specifying, for example, which locations are occupied by the stones, and of course, the remaining locations must be occupied by the sticks. Once we understand this key principle, the generalization is very, very clear, and we immediately write down the general answer. So now let's suppose we start with n indistinguishable balls and r urns. Arrange the urns from left to right. Fix the endpoints. How many separators, how many sticks do I have? 1 less than the number of urns, r minus 1. How many stones do I have? Well, it's the number of balls, n. How many locations do I have to distribute my sticks and my stones? N plus r minus 1. Of these locations, you have to specify which n are taken by the balls. The remaining ones, of course, are taken by the sticks, the urn boundaries. And of course, you have a binomial coefficient. N plus r minus 1, choose n. We now have a complete description of the number of ways in which we can distribute n indistinguishable balls into r urns. We now put everything together. There is no reason to believe that any one distribution is any more likely than any other. So we make the natural assumption that these configurations, these distributions, are all equally likely. So now we have n plus r minus 1, choose n possible ways of creating these occupancy configurations. The chosen occupancy configuration, K1 through Kr, is one of them. And therefore the chance of observing that particular occupancy configuration is the reciprocal of n plus r minus 1, choose n. Bear in mind again that these occupancy numbers are not negative, and they must inevitably add up to the number of balls in the system. The key here is that the balls are indistinguishable. Now, this is theory. This is nice. This was published in 1924 by Bose and by Einstein. But is it real? Okay. What is the worth of such a theory? Of course, the essential worth of a theory is in its fit to observed reality. And in this model turned out to be hugely successful. A wide range of elementary particles and composite particles follow this law articulated by Bose and Einstein. These particles are called bosons in honor of Satyendranath Bose. The nomenclature was created by Paul Dirac. And bosons, for those of you who know a little physics, are particles which have integer spin. For the rest of us, what does this mean? Well, there's a wide range of elementary particles which fit this model. Common examples are photons, the carriers of light. The gauge bosons, which are the carriers of force. These include the gluons, which mediate the strong nuclear force, and the W and Z bosons, which mediate what is called the weak nuclear force. These are force-carrying particles. The Higgs boson. This was a particle which was postulated around the middle of the 1960s to be the particle which confers mass as we observe it. The existence of this particle is key for 20th century physics to work as advertised. And ever since it was postulated in the 1960s, a massive particle hunt was underway to try to determine whether this particle actually existed. And remarkably, in 2013, at the Large Hadron Collider in Geneva in Switzerland, physicists announced that they had discovered this elusive particle, the Higgs boson. Because of its fundamental nature, this particle is sometimes called the God particle. All these are examples of bosons, fundamental particles which obey the Bose-Einstein statistical law. Einstein observed that this kind of law also applies to composite particles, larger particles. For example, things like the helium-4 isotope and the carbon-12 atom. These are examples of larger structures, larger particles, which obey this basic law. At the heart, the particles called bosons have this principle in mind. They are represented by indistinguishable particles distributed in a non-interacting fashion across possibly many urns. You discern this kind of statistical phenomena at the particulate or the quantum level. Now, a key element here is that these particles are non-interacting. Photons, for example, don't really interact with each other. And that these particles can comfortably occupy the same urn. They are not snobbish or exclusive. So many particles could land in one urn. Now, this led Einstein to conjecture in 1924 that you could have a state of nature, very, very strange state of nature, where if you cool the system down to close to absolute zero, that bosons could end up falling into a state which was as comatose as possible, as still as possible for a quantum mechanical particle. Now, no quantum mechanical particle is absolutely still. It's got little twitches. It moves. It moves. That's the nature of the beast. Okay, this is one of the strange features of a quantum mechanical view of the world, that there's randomness everywhere, there's twitchiness everywhere. But if you try to eliminate the twitchiness as much as possible, close to absolute zero, then Einstein realized that this kind of model gave rise to this new form of matter, something that today we call a Bose-Einstein condensate, where the particles at the quantum level all sit together and form a stew where macroscopically this soup will exhibit quantum kinds of behavior. Now, this is where the worth of a theory comes into evidence. It makes predictions. Could this actually be realized? Well, the hunt from 1924 took 70 long years, 71 to be precise. But in 1995, physicists at Boulder, California, constructed a Bose-Einstein condensate using rubidium atoms cooled to near absolute zero. This was a triumphant vindication of the theory, which had been a century in the making. And since then, other Bose-Einstein condensates have been constructed and observed. As late as the year 2010, a Bose-Einstein condensate of photons, the fabric of light, was constructed. This is a marvelous story, okay, and it actually ends up in a Nobel Prize winning story for these discoveries. But it is not a complete story. Just a couple of years after Bose and Einstein published their paper, physicists realized that these phenomena described by the Bose-Einstein statistics don't apply to certain other common particles. This will be the next part and the final part of our story.